Welcome to this lecture number 8 on this NPTEL course on fluid mechanics for for undergraduate students in chemical engineering. And until the last lecture, we discussed fluids under static conditions, the variation of pressure in a fluid under static conditions, the forces that are experienced by objects submerged in a fluid under static conditions, and so on. Before I move on to the new topic, I am going to quickly recapitulate the key results that we discussed so far. So, under fluid statics, we first saw that if a fluid is under static conditions, okay, if you take any volume element, okay, this is a volume element in a fluid, okay, then the force that is exerted by the fluid that is present outside on the fluid that is present inside is purely normal, and it is acting in a compressive sense. Okay. So, the force that is exerted by the fluid that is present outside on the fluid that is present inside is denoted by R, and if you take any particular point on this volume element, this force is a function of the unit normal. So, since if you take any point on the surface, the unit normal point outwards, that is from inside to outside, the force on a static fluid element acts from outside to inside. So, this force is written as P times minus n, because minus n is the direction at which the force is acting and P is the magnitude of the force. Well, it is more appropriately, this is the magnitude of the compressive force per unit area acted upon by the fluid outside on the fluid that is inside on the surface that separates the outside and inside. So, this compressive force per unit area, the magnitude of it is called the pressure in a fluid, okay. And we saw that this pressure has units pascals. So, 1 pascal is 1 Newton per meter square, okay. And then we said that if you have a fluid, okay, that is under the influence of a gravitational field. So, we took a coordinate system x, y and z, and gravity acts in the direction of minus z direction. So, if you look at, if you want to write the gravity vector, it is minus g times k. The g is the acceleration due to gravity, it is 9.8 meters per second squared on the surface of the earth, and k is the direction of the positive z axis, minus k is the direction of negative z axis. So, g is minus the g vector is minus g times k. So, we have a fluid that is present under the influence of a gravitational field, and we said that by taking a tiny volume element of a fluid, we can show that the fundamental equation of hydrostatics is minus del P plus rho g is equal to 0. Okay. So, this is the fundamental equation for a fluid under static conditions. The physical interpretation for this equation is very simple. Rho g is the force per unit volume due to gravity. This is the weight of the tiny volume element, okay. And this is del P is the net pressure force minus del P is the net pressure force per unit volume acting on the fluid element, and since the fluid element is at rest, the sum of all the forces must be 0, and that is what gives rise to this simple balance. Now, normally this equation, if you should remember that this is a very general equation, in the sense that this is valid for any coordinate system, not necessarily the rectangular coordinate system depicted in this cartoon, valid for any coordinate system. But if you want to solve a problem, you would refer this equation with respect to this Cartesian or rectangular coordinates x, y, z and g pointing like this. So, we found that minus dp dz, okay, minus rho g is 0, or dp dz is minus rho g. Okay. So, if you want to integrate this equation, we have to assume certain things about density. If you assume incompressible fluids for which density is independent of pressure, okay, rho is independent of pressure P, then we can, and since g is a constant, both rho and g are constants in this equation. So, we can easily integrate this. So, you get integral dp between any 2 points P1 or P0 and P is minus rho g integral z0 to z dz. So, P minus P0 is rho g times z0 minus z. Now, in most applications you will have a pool of liquid, that is water, let us say, and that is open to an atmosphere, air at atmospheric pressure. Okay. So, this is P atmosphere. Okay. This is the free surface that separates the liquid from air, water from air, for example. So, at this point the pressure is P atmosphere, it is known. Okay. So, our coordinate system is aligned like this, x, y, z, where z is increasing in this direction. So, if you refer z naught in this equation as the free surface, z equals z naught, okay, and any point z is this distance is z naught minus z, and we can call that as h. H is the depth of the liquid from the free surface, is the depth of liquid from the free surface. In which case we can rewrite this equation as P minus P0 is P atmosphere, because that is the value of the pressure at z equals z0. Okay. P minus P atmosphere is rho g h, or P is P atmosphere plus rho g h. This is a fundamental equation valid for incompressible fluids, because we assume rho is constant. Okay. And it is valid when gravity is in the direction of minus k. Okay. So, these are the two key assumptions, and then this equation is very useful in solving many problems. One example is what we did was to show, suppose you have a free surface and then you have a solid surface, planar solid surface, and then we are interested in finding the force, net force, effective force on this solid surface. Okay. Okay. And that force will act normally. What is the magnitude of the force, which we call Fr, and what is the line of action of the force? So, both of this we calculated by simply, so this is a cross section of a planar surface like this. So, this is a planar surface, and you take a tiny area element, and then we find what is the, let us call this dA, the pressure, the force acting is PdA, and then you integrate this, you get the total force Fr. So, it is as simple as that, and then by equating the moments, okay, we found what is the line of action in the last lecture. The next application of this simple formula, that P is P atmosphere plus rho g h, was to calculate the force on a submerged object. Suppose you have a solid object that is submerged in a fluid, and this is atmospheric pressure. Okay. The fact is that because gravity is acting in this direction, okay, the force, the pressure on this side will be smaller than the pressure on this side, okay, because of this column of liquid that increases the pressure by rho g h. Okay. Then we saw that by taking a tiny cylindrical volume element, and we saw that the net force acts upwards, okay, because of the fact that the pressure here is more than the pressure here, and by taking many such tiny cylindrical volumes over the entire volume, we saw that the net force acting upwards, in the direction upwards to the gravity vector, that is the upward direction, upwards on a submerged object is simply rho of the liquid, density of the liquid, times g times the volume of the liquid that has been displaced by the solid. Here the entire volume is submerged. So, it is the entire volume of the solid itself, volume of the liquid that is displaced by the solid. If the object is partially submerged, like here only this part is submerged, okay, then this is a floating object. Okay. By the way, this force is called the buoyancy force, and this principle is the Archimedes principle. So, for a floating object, the displaced volume is, let us call it V displaced. Okay. So, if an object is floating, that means that it is not completely sinking into the liquid and gravity is acting down. If m is the mass of the solid and g is the acceleration due to gravity, mg is the weight of the object, solid object, weight of the solid. This must be balanced by V displaced times rho times g. Okay. Now, the mass of the solid is nothing but rho solid times V solid, the volume of the solid times g is equal to V displaced times rho liquid times g. This is a condition for floating, condition for a body to be at equilibrium, for a body to be floating in a liquid surface. Okay. So, this is Archimedes principle. What I will do next is to illustrate this with a slightly more involved example. So, let us try to apply this principle for a following problem. You have a huge a swimming pool, let us say, a huge body of water. Okay, this is the water level. Okay, this is water, and you have an object, let us say a raft, that is floating, and over the raft there is a barrel, a cylindrical barrel. This is a raft, this is a barrel. Okay. So, this is water. So, this is gravity is acting in this direction, and let us say the displaced volume is V in this case. Let us call this situation case A. Let us consider two other situations. The second situation is where you have same barrel and raft, but the barrel and the raft are floating separately. They are partially submerged, both are floating. So, let us call the displaced volume as V raft and this is V barrel. Okay. So, they are floating separately, let us call this case B. Okay. And the third situation is like so. You have free surface of the water, okay, and then you have the barrel, but sorry, you have the raft, but the barrel is such that it is completely submerged. Okay. So, let us call this displaced volume V r in both the cases of the raft. So, this is the displaced volume of the barrel. Okay. Let us call this case C. Okay. Now, in comparison these three cases, what is the level of water of case B and case C with respect to the level of water in the swimming pool in case A? That is a question that we are going to answer by using the Archimedes principle. So, let us consider case A. Okay. Here the both in case A both barrel and raft are floating, okay, but the displaced volume is only due to the raft. So, by using Archimedes principle, okay, the net force downwards is given by the sum of weights of the raft and the barrel times g. This must be balanced. If this combination is to be floating, then this must be balanced by buoyancy upwards, the buoyancy force upwards, which is nothing but rho water, which I denote as rho. This is the density of water, okay, times V r. Let us call it just V. That's the notation we used, times g. Okay. So, condition for floating in the first case, case A, is mr plus mbg is rho vg. Okay. In case B, barrel floats separately, the raft and barrel float separately. Okay. That means that m raft times g, okay, is V raft times rho g, and m barrel times g is V barrel times rho g. Okay. These two must separately hold for both these things to float separately. We can add these two equations, m r plus m b times g is equal to V r plus V b times rho g. Okay. Let us call this equation 2, let us call this equation 1. When I compare these two equations, okay, this implies that, okay, and V r, m r plus m b is the same on the left side. So, rho V g must be equal to, the right sides must also be the same, must be equal to rho V r plus V b times g. So, if I cancel rho, the density of water, and acceleration due to gravity, I get that V is V r plus V b. That is, in case B, where the barrel and raft are floating separately, okay, here the net displaced volume is the same as the total displaced volume in case A. So, no change in the water height, in the level of water in the swimming pool. Okay. That is a conclusion we can come to, okay, just by applying Archimedes principle to these two cases individually. Let us go back to case C. Okay. Now, in case C, you should remember that the raft is floating. So, if the raft is floating, then the net weight downwards must be balanced by buoyancy force acting upwards. Rho is the density of water, but this is raft floating condition. But the barrel has sunk, okay, barrel is sunk. That means that the net downward weight must be greater than the buoyancy force. Okay. This is the entire volume of the barrel, okay, g. So, if I add these two equations, then I get m r plus m b g must be greater than or equal to rho V r plus V b g. Let us call this equation 3. Let me rewrite equation 1, which is m r plus m b g. This is equation 1 that I just derived few minutes back, is equal to rho V g. Okay. This means, if this is the case, this implies that if the left side of this is greater than this, okay, this means that this is identically equal to this. So, rho V g is greater than, okay. So, this is, there is a g here, is greater than rho V r plus V b g, or V is greater than V r plus V b. So, this is equation 1 from case 1, where this is the displaced volume when the raft and the barrel are floating in this is case A. Now, in the case C, only the raft is floating, this is the displaced volume of the raft, entire barrel is sunk. Okay. So, this implies that the level will fall, this is case C, water level will fall in case C, because the displaced volume here is less than the total volume when the raft and barrel both were floating. So, compared to these two cases, this water level will be smaller because the displaced volume here is smaller compared to the displaced volume in case A. So, this is a slightly counterintuitive result, because you have a situation where this barrel is completely sunk and you may intuitively or instinctively think that this water level will rise here compared to case here, but by a careful application of Archimedes principle we can show that it is not the case, in fact it is opposite. Okay. Now, one last topic in fluid statics. So far I have been discussing fluids under static conditions under the influence of a gravitational field, but in many chemical engineering applications you encounter a fictitious body force called the centrifugal force, which happens, this force happens because of rotation. Suppose you have a bowl of liquid like water and you rotate it, this whole bowl is rotated at a very high speed, okay, let us say omega. Okay. Now, if you have liquid in it and it is not completely filled, then this liquid, the centrifugal force, if you remember from mechanics, acts from the radial axis to outwards. So, this is the direction of centrifugal force. So, the centrifugal force on any fluid element tends to throw the fluids towards the outside. So, you may imagine that if the bowl is not fully filled, then this water, initially the water level will be like this, okay, it is partially filled. Now, after rotating, okay, this water will just be thrown close to the surface, and this situation will happen when gravity is very small compared to the centrifugal force. Okay. When the centrifugal force is so large, when the rotation speeds are so large, then this liquid will be completely thrown towards the end of the towards the rim of the container, okay, the bowl. Okay. In this case, the entire mass of liquid will rotate like a fluid. Okay. Now, imagine this is the axis and this is the wall, this is the wall of the bowl, okay, and let us call this radius as R2, and this is the interface, this is liquid. So, I am just trying to blow this region up here, okay, and let us call the distance of radial distance of the interface from axis as R1. Okay. Now, the centrifugal force, if you take any tiny fluid element, well, it is actually annular, it is an annular element. So, because the geometry is cylindrical, so the fluid element will be annular, it is a ring like element. Okay. So, if you take any fluid element, there is a unbalanced centrifugal force acting radially outwards. So, if the fluid is rotating like a rigid object, okay, so there is no relative motion between two fluid elements, then you can think of the entire thing as though it is a solid like motion. So, it is under static conditions, even though it is moving like a rigid body, okay, there is no relative deformation. So, there are no shear stresses. So, the only stresses are purely normal to the fluid elements. So, the pressure. So, the pressure must vary accordingly to balance the body force due to centrifugal forces. So, how does one calculate this? The differential force on an element, okay, on a volume element, differential centrifugal force, on a volume element is centrifugal force goes as mass times the radial distance squared times the angular velocity squared times the radial distance, okay, m r omega squared. So, if you take a differential volume element, so it is a differential mass dm times omega squared, it is the angular velocity squared times r, this is the angular omega is the angular velocity in radians per second. Okay. So, this is the mass of the volume, tiny volume of the differential volume element. If you take a cylindrical volume element, its mass is dm, is the volume is 2 pi r. So, this is r, at any radial distance r, you consider a slice, cylindrical slice, and let this height be b of the cylindrical element. So, 2 pi r b is the surface area of the cylinder at R, inner cylinder, times dr, which is the thickness, because it is a tiny thickness we are considering. Okay. This is the volume, okay, times the density, okay. This is the mass, this is dm. So, df is nothing but 2 pi r b, okay, times dr rho times omega squared r. Okay. This is the differential force on a volume element due to centrifugal forces due to rotation. Okay. Now, this must be balanced by differential pressure. So, if you take a tiny slice at the cylindrical size, there is a differential force that is acting like this. So, the pressure buildup must act such that it balances. This is the pressure acting in this direction. Okay. The pressure must tend to counteract the centrifugal force that acts in this direction. Okay. So, the pressure must balance, the change in pressure must balance this centrifugal force, which tends to now let me simplify this slightly. Okay. So, it is 2 pi r squared omega squared b rho dr. Okay. That is the this is the force. So, the pressure is force divided by area, area is 2 pi r b. So, this is the force. So, pressure is force divided by area. So, let me cancel 2 pi r b. Okay. So, dp is nothing but, so 2 pi b and then 1 r cancels, is rho r omega squared dr. Okay. Okay. So, integral dp, if I want to find the pressure distribution or difference between any 2 points, I integrate this over the 2 points. So, between P1 and P2, between any 2 radial locations R1 and R2, no longer small, is R dr. So, this implies P2 minus P1 is rho omega squared by 2 R2 squared minus R1 squared. This is after integration. Okay. So, this is a important result where the pressure variation is now happening in a rotating fluid, where the body force is due to centrifugal forces and not due to gravity, and this is in the limit when the centrifugal forces are large compared to gravitational forces. So, we have neglected gravity compared to centrifugal forces, Okay. So, just as gravity acts on objects, okay, so in a gravitational field, okay, centrifugal forces can also act on objects, and the centrifugal force, okay, will tend to accelerate particles with higher density or elements with higher density, and they will be thrown towards the wall because the magnitude of the centrifugal forces are larger, and these are used in many separations. Okay. So, if you want to separate two liquids, two immiscible liquids with different densities, okay, one way is to take these two liquids and put them in a centrifuge, which is basically a bowl that is rotated with very high speeds, and then because of the centrifugal action, okay, the liquid of higher density will be thrown towards the wall, and the liquid of lower density will be more towards the center, and then you can simply separate these two away just based on density difference. Okay. The same thing can be done due to gravity, with the help of gravity also, that is called gravity based separation, but the driving force, which is because of acceleration due to gravity g, okay, is very small, it is fixed rather, but in the case of centrifugal forces we can vary the centrifugal acceleration at our will by changing the angular velocity of rotation, and you can achieve faster rates of separation between these two fluids. Okay. So, this really completes my emphasis on fluid statics. So, the next topic I am going to discuss is fluid kinematics. Okay. So, firstly, what is kinematics? In general, in any subject that deals with mechanics, whether it is solid mechanics or fluid mechanics or particle mechanics, whatever subject you have it. Okay. Mechanics deals with, as I told in the beginning, forces and the motion that is caused by forces. Okay. So, mechanics is broadly divided into two parts. One is kinematics. Kinematics is the subject that deals with description of motion without worrying about or without reference to the forces that cause them. Okay. So, that is the first thing, is to be able, before understanding how forces cause motion, the first step is to first understand how to describe the motion per se, the motion itself, and once we have the necessary tools to describe motion, then we can go ahead and study how forces cause motion. That subject is called dynamics. Dynamics relates motion to forces. Okay. So, these are two branches of mechanics, and so firstly we will have to understand how to describe fluid motion. So, we will do kinematics of fluid flows, because in this course we are interested in motion of fluids. So, we will first discuss kinematics of fluid flows, then we will proceed to dynamics. Okay. Okay. Now, useful. So, firstly let us try to understand what are the various options we have to describe fluid flows. Okay. Now, remember that we have already taken the continuum route or the continuum approach, wherein we are saying that the fluid is a continuous medium, and you can identify each and every point in the fluid and ascribe unique properties to a point, such as velocity, pressure, temperature, density, and whatnot. Okay. All kinds of properties can be attributed to each and every point in the fluid, and these and these various variables such as pressure, density, and so on, they are smoothly varying functions of spatial coordinates and time. Okay. This is the essential crux of continuum hypothesis. Okay. Now, what do I mean by a point in a fluid? Okay. Okay. So, in this context, the notion of what is called a hypothetical fluid particle helps, okay, in the continuum picture. What is a fluid particle? Well, imagine, let us say you have a box containing a liquid like water, and it is stationary initially. Okay. Let us say we take a colored dye and then mark a fluid here, and then take another colored dye, mark a fluid here, take another colored dye and mark a fluid here, take a dye of another color and mark a fluid here, and so on. Imagine that you are marking fluids with colored dye, and let us assume that the dye molecules do not diffuse, so that the dye stays put. I mean, it does not, if you drop a colored liquid like ink, of course, you know that it is going to dissolve or diffuse in water, but let us assume that the diffusivities are so small for our time scales of interest here, that you can imagine that the dye does not dissolve at all. Okay. We can imagine the dye to be insoluble in the liquid that we are considering. Okay. Now, this is the time initially at time t equal to 0. Okay. So, you are imagining that at each and every point that you can resolve in your scale of measurements, you can point a dye and you can visualize its motion. Okay. So, this is at time t equals 0. At a later time, okay, all these points may move. Okay. For example, this blue colored dye, okay, let us say this blue colored dye element will move. So, let us use pink color for, okay, at a later time. So, I will try to draw the later time picture with a open circle. So, time t equal to 0 is closed or filled circles. Okay. A later time, okay, at time t it is open circles. That is how I am going to indicate the motion of various points, okay, in the fluid, and the fluid is moving due to presumably due to application of some forces. So, essentially we have a bunch of points that are marked by dye, colored dye, and we are assuming that the dye molecules do not diffuse, okay, and so that they just stay put wherever they are, and at time t equal to 0 when there is no force forcing on the fluid, and at a later time, okay, due to application of some forcing the fluid is under motion, okay, and when the fluid is under motion all these points will move to some other points, okay, some other locations, okay, all these colored points will move to some other locations. For example, this may go to here and so on, okay, and this red dot will the red dot will move here, this orange dot will move here, and this yellow dot may move here, okay. So, these are the locations of these various points, okay. So, notice that I am using closed circles for, okay, initial time, the location at initial time of various dye elements, and I am using open circles for, okay, just for the sake of clarity I am exaggerating the size of these points, okay, so that you can see them easily, okay. So, this can happen, okay, that various points that were initially located at some locations denoted by closed circles, okay, will move eventually upon fluid motion, okay, to some other locations. Now, these can be thought of as the location or this, let me just, okay, these points can be thought of as fluid particles. Such dye spots, okay, which can be used to identify location of fluids at various points in the fluid at initial time, and the subsequent motion can be thought of as a fluid particle. And within the continuum hypothesis, a fluid element can be comprised of fluid is infinitely smooth, okay. So, there is no discreteness in a fluid. So, you can resolve a fluid to any length scale you want. So, there are infinitely large number of fluid particles corresponding to each and every point in space within the continuum hypothesis. And just by way of illustration, I use the notion of coloring the fluid with a dye element, a dye substance, to visualize the motion. But the idea is you can think of it as a mathematical framework where at time t equal to 0 you have various locations in the fluid, okay, which are marked by their initial locations, and at a later time due to application of forces all these points will start moving and they will tend to occupy various different locations in general, okay. So, this is the notion of a fluid particle. So, in general at time t, okay, you have a fluid particle which is moving at a later time, okay, this time t equal to 0 initially, let us say there is no motion initially, and upon application of some forcing, okay, this point moves in spatial coordinates. So, you always have, let us say, an x, y, z coordinate with respect to which we are describing a motion that is implicit. So, just to be complete, let me just put a coordinate system there. So, there is a point that is located at time t equal to 0 and it is moving due to application of forces to some other location. This is the current location, let us say at time t, okay. This is what is called a particle trajectory, okay. But there are infinitely large number of such points. So, let me just show it with some other color. So, there are large number of such points because you can assign to each and every point in space a point, and all these points will start moving upon application of forces. So, one way to describe fluid motion is to consider all these points, okay, label all these points at their initial location before application of forces. Okay. So, let us label all points in fluid in the fluid based on their initial positions. Okay. So, let us call the initial positions of a point as, so if you put a coordinate system, okay, any point will be denoted by a vector x. Okay. So, this is x, y and z coordinate system. So, x p, okay, 0, x 0 stands for initial time t equal to 0, and p denotes a fluid particle, the subscript p denotes a fluid particle. Okay. So, x p 0 is a vector. So, it is comprised of 3 coordinates x p 0, y p 0, z p 0 in a Cartesian coordinate system. Okay. So, this is nothing but the location of the trajectory of the location of the particle, position of the particle at time t equal to 0 is x p 0. Okay. This is the initial location of various particles, various fluid particles. Now, upon influence of forces, the location of these particles at time t, okay, will change in general, of various particles will change, okay, due to fluid motion. Okay. Now, this x p of t, okay, the current location is a function of the initial locations. Okay. So, once I tell you what are the initial locations, okay, of various particles, okay, the current location of the various particles will be a function of the initial location, because a point that was here will move here, okay, a point that was here will move to some other location. Okay. This point can never move here, and likewise this point can never move here in a given set of flow field, in a specified flow. Okay. So, each point which started out initially at x p 0 will eventually reach a unique x p at time t. Okay. So, the current position of various fluid particles will be a function of their initial positions. Okay. Now, if I know this functional form, okay, sometimes people just write this as x p of t is x p of x p naught and time, that is the function itself is denoted by the same symbol. Okay. Now, if I have this functional form, how the current position varies with initial position and time, then I can calculate the velocity of a fluid particle at time t. Okay. Velocity of a fluid particle x p naught at time t. A fluid particle is identified by its location at time t equal to 0. So, let me use some of the color here. So, at time t equal to 0, a fluid particle is at x p naught, and this particle moves here. Some other particle which was here would move there, okay, at time t. So, each particle, so this particle which is at time t here, okay, is labeled by its location at time t equal to 0. Okay. So, each particle is labeled by their initial locations. Okay. So, this is the velocity of a particle which was at time x p 0 at time t equal to 0, and the velocity of that particle at time t is nothing but the rate of change of its position dxp by dt, okay, keeping xp 0 constant. That is, you are fixing the same particle, you are following the same label in some sense, and you are asking what is the velocity at time t. Well, it is simply the rate of change of its position vector, which is xp. Okay. Now, such a description is called, such a description of fluid flow, wherein you are identifying various particles by their locations at time t equal to 0 and merely following the positions of various particles as a function of time, is called the Lagrangian description. It is called the Lagrangian description in fluid flow. What is the Lagrangian description? Well, here the independent variables are the position, the initial position of various particles, that is a label, and time. Okay. So, all properties such as, suppose, velocity of a particle is a function of its initial position and time. So, what is this? This is the velocity of a particle which was at xp 0 at time t equal to 0 at, and as the particle moves at a later time, what is its velocity. So, you are following various particles, okay, and then you are inquiring what is their velocity, what is their acceleration, what is their density, what is the pressure, what is their temperature, and so on. So, the independent variables in a Lagrangian description are, so if you have any function, okay, any property, it is given as a function of the initial position of the particle, which is essentially serving as a label of the particle, and time. Okay. Now, so not just for flow variables, even you can think of temperature in a fluid, okay, in a moving fluid. So, this is the temperature of a particle which was at time t equal to 0 at xp 0 at a later time t. So, various particles as they move, okay, their properties such as density, temperature, concentration, and velocity, and many other things will change. Okay. But you can describe the change based on their initial coordinates. This is the essential idea behind Lagrangian description. So, once I have this motion, how the trajectory of the particle changes, various particles change as a function of time, then I can get velocity of a particle which was at xp 0 at time t equal to 0 at a later time t is nothing but the rate of change of its position by keeping xp 0 same, that is, you are following the same particle. Okay. Now, acceleration of a particle is nothing but the rate of change of its velocity keeping the same particle. Okay. Such a description is also called sometimes as the material description or the Lagrangian description. Okay. Now, this is one way of describing fluid motion, but this is not the only way, or this is neither is this the most useful way. What is normally done in fluid mechanics is what is called the Eulerian description. Okay. So, what is the Eulerian description? Here we place a lab coordinate frame in our lab x, y, z and measure various properties such as velocity in the fluid as a function of the three spatial laboratory coordinates and time. Okay. So, velocity is measured not as a function of various particles, not by following the particles, fluid particles, but by merely saying that what is, suppose I put various flow measuring velocity meters, so to speak, at various points in space, and then I measure velocity at each and every point, okay, as a function of time. So, that description is the Eulerian description. This is also called spatial description for obvious reasons, because we are not describing properties of the fluid such as velocity, acceleration, pressure, density, temperature as a function of by following the various particles. So, in the Lagrangian description, by labeling a particle, okay, when I say temperature of a particle, what I mean is that as I follow the particle, how is the temperature changing with time, that is the Lagrangian description. In the Eulerian description, we are not following the particle anymore, fluid particles anymore, we are simply keeping a stationary frame of reference, a lab frame of reference, and this could be stationary or it could move with a constant velocity, that depends on the nature of the problem. For simplicity, let us keep a fixed coordinate system in our lab, and then we can measure various quantities such as velocity or temperature or pressure at various points with respect to this coordinate system as a function of time, and report quantities like how does the temperature change at various points in the fluid as a function of time. So, what is T of x t at a given location? If I fix x, so if I have a 3 Cartesian coordinate system, I can fix x. At a fixed x, how does the temperature change as a function of time, okay? Or at a given time, how does the temperature vary as a function of x, y, and z. So, this is called the spatial description in fluid mechanics. Okay. Now, such quantities are called fields. This is called the velocity field, where the velocity is expressed as a function of the 3 spatial coordinates and time. This is called the temperature field. Okay. Now, what this description does is that suppose I put a thermometer, suppose I have a fluid that is flowing, I put a thermometer, say this is a thermometer, okay, and I measure T at a given location, let us call this x, okay, and time. Okay. What this is measuring is at a time t, it is measuring whatever. So, the fluid is continuously flowing, a fluid particle will occupy this spatial location x at a time t, and T of x t will be the temperature of that fluid particle, denoted by this pinkish violet circle, okay, which happens to occupy the spatial location at time t. At a later time, okay, t plus delta t, a slightly later time, okay, at the same spatial location, okay, this point would have moved, let us say here, this point which was here at x, okay, would have moved here, and some other point would have come and occupied the location x. Okay. This is the same location x. So, let us call this a vector x. Okay. So, different fluid particles, the key to understand here is that different fluid particles will occupy spatial positions, okay, at the same spatial position at different times by virtue of fluid motion, okay, because the fluid is continuously moving or flowing. So, what the thermometer will measure at a given spatial location is merely a record of the temperature values at that location, okay, as a function of time, and this does not correspond to the temperature of a fluid particle. So, the Eulerian description gives a very completely different viewpoint compared to Lagrangian description. In the Lagrangian description, you would follow the same particle, okay, as a function of time. So, okay, whereas in the Eulerian description, you are not following the same particle, you are merely sitting at the same point in space, and you are recording various properties such as such as temperature in this particular instance. So, we are measuring the properties of various fluid particles, not the same fluid particle. So, we will stop here and we will continue in the next lecture further. Okay. We will see you in the next lecture.